Okay, IB topic 3, periodicity. This is a nice animation of the elements. It's from a app that I have. Let me show you. It's kind of cool. Where if I click on any of the elements, it'll pull it up. A nice picture of it, information about it, and you can return home. There's a website. Same thing. It doesn't have the animated GIFs for the elements, but same layout and same information. I'll put the link on today's lesson module. Now, topic 3 starts with 3.1, which is the periodic table. 3.2 is periodic trends. 3.1 is just getting to know the periodic table. I think most of you already have most of that down. Let me show you a few of the videos from the IB video tutorials. They're pretty good.
This clip shows the date that elements were observed, predicted, or their earliest usage. I got this data from Wikipedia.
So if you look at the bottom, he's putting in the elements as time goes by when they were discovered.
And there's a big gap now of about 2,500 years until the next elements were discovered. The first one being phosphorus. Some man boiled urine until it glowed and discovered phosphorus. Notice that the reactive metals such as potassium and sodium only arrived when electricity was finally used to break them from their compounds. Noble gases were towards the end, and the transuranic elements could only be discovered once the technology had increased far enough, approximately the time of the Manhattan Project. The modern periodic table has 7 horizontal rows called periods. Period 8 will start with the discovery of element 119. The vertical columns are called groups. The word periodic is used to denote the many patterns in the table.
Okay. Key features of the periodic table. Now, the periodic table you're looking at here is straight from the IB data booklet. If you were to test in IB chemistry, you have the data booklet on one of the exams, a couple of the exams, but only one this year. And this is the IB data booklet. So this is the IB periodic table from the data booklet. It's a little different than the one that you have. Notice that the numbers along the top here are just numbered 1 through 18. It doesn't use the system that is quite handy in learning the number of valence electrons. So this is 1A, 2A, 3, 4, 5, 6, 7, and 8A, as we'll see in a few minutes. Okay, the first key feature, elements are arranged in order of increasing atomic number. So hydrogen is 1, helium is 2, lithium 3, all the way to neon 10, to sodium 11, all the way to argon 18, etc. 2, groups or families are vertical columns numbered 1 through 18. So group 1, group 2, group 9, group 15, etc. Periods are horizontal rows going across. So this is the first period, the second period, down here the 6th period, but notice the way that IB denotes the lanthanide series is actually right here. So they have this little T here, which is that little T there, across. So period 6 is actually this, and then goes all the way through here, and then picks up here. All of that is period 6. And from our last notes, you know this well, we can look at the periodic table in terms of the SPD and F blocks. This is right from your IB chemistry book, textbook, page 72. The SPD and F blocks. So you need to be able to discern if an element is an SPD or F block based on its location. And it's really fairly easy to do. The first 2 groups are the S block. Don't forget, though, that helium, in that sense, would also be referred to as an S block element. Though again, it's a noble gas. It rightfully belongs over here. It has the same properties as the other noble gases in that it's very unreactive. But anyways, these are the transition elements, and this is the inner transition elements. Okay, main group elements are the S and P block elements. These are the most abundant elements in the universe. So group 1, 2, 13 through 18. But again, that numbering system is really quite handy, is 1A, 2A, 3A, all the way to 8A. And we'll talk about valence electrons in a minute. It's a nice little pie chart of the most abundant elements in the universe. So we're looking at the entire universe. Hydrogen, 75%, helium, 24%, everything else, less than 1%. But the S and P block elements are the most abundant of all the elements. The most abundant elements in the Earth, and so you can kind of look at this, oxygen, iron, silicon, sand is almost all silicon dioxide, so silicon and oxygen, magnesium, aluminum, etc. Valence electrons, the outermost electrons of an atom, only found in the S and P sublevels. So only the electrons that belong to the S block and the P block are valence electrons. Okay, now let's look at magnesium as an example to determine valence electrons. So this is the electron configuration for magnesium. So we have 2 electrons in the first energy level, and we have 8 electrons in the second energy level, and we have 2 electrons in the third energy level. Those last 2 electrons are our valence electrons. This is referred to as the valence shell. The valence shell is simply where the electrons reside. Where the valence electrons reside. All of the electrons interior to the valence shell are referred to as core electrons. When we're talking about the chemical properties of the elements, it's always the valence electrons. Remember, atoms tend to lose, gain, or share electrons to have the configuration of a noble gas. It's the valence electrons that are lost or shared. Core electrons are pretty much locked in place. They're still dancing around, but they will not be easily removed from the atom. Certainly not in a simple chemical reaction. Practice. Underline the valence electrons for arsenic. Okay. So here's the electron configuration for arsenic. When you pause the video and see if you can determine which are the valence electrons. 3, 2, 1. They are the 4s and the 4p. Remember, the valence electrons always belong to the outermost energy level. And so all you have to do is to look to see which numbers belong to the highest energy level. In this case, it would be the 4th energy level. Now remember, the 3D is filled after the 4s and before the 4p. Nonetheless, the 4th energy level are where the valence electrons are for arsenic, whether it's both just S or S and P. Arsenic is in group 15 or 5A, so it has 5 valence electrons. So that's what's kind of nice about that numbering system that you have on your periodic table. If you just look for that 1A through 8A and just whatever column it's in, the element's in, that's how many valence electrons it has. All the other electrons are core electrons. Okay, now one of the things you need to be able to do is name the parts of the periodic table. So we have the alkali metals, it's group 1. Now that does not include hydrogen. Hydrogen is kind of like an orphan. It doesn't belong to any family. It's a family of its own. It's very unique. But it is a group 1 element in that they all have 1 valence electron, but it is not an alkali metal. So group 1, other than hydrogen, is alkali metal. Group 2 is the alkaline earth metals. We have the transition elements. And then boron, carbon, nitrogen, and oxygen families are just named after the first element in those families. So those are kind of easy. Boron family, carbon family, nitrogen family, oxygen family. But it's not the fluorine family. Those are the halogens. And then the very last group, the noble gases. Then we have the lanthanide series. So this is a series, not a group or a family. The lanthanide series and the actinide series. And this is your periodic table. Now, on your periodic table, you have, yours isn't colored. You can see, and it's kind of shaded a little bit, but you can see that these are the metals. And then we have the nonmetals. Hydrogen is also a nonmetal. You have to remember that. Hydrogen is a nonmetal even though it's over here. It's over here because it has one valence electron. And remember, we have a little staircase that we draw that separates the metals from the nonmetals, and every element that runs along that little staircase is what we call metalloids or semimetals. So it's easy to remember if you just right below boron, just draw a little staircase, over one, down one, over one, down one. I have kids do that in my first year class, and you may have already done that, but if you haven't, on your periodic table that you have, I would encourage you to do that. Just use a dark pen or pencil and make sure you have that little staircase there. Every element on either side of that staircase is a semimetal except aluminum, which is kind of easy to remember. Aluminum is a metal. Aluminum foil, aluminum cans is a metal. But every other element that runs along that little staircase are semimetals. And then you should know the states of the elements. Now, this is in normal conditions, and usually it's 25 degrees Celsius, which is about 77 degrees Fahrenheit. So if we were to have any of these elements, what state would it be in? Would it be a solid, a liquid, or a gas? And you can see that they have little icons here that they use to represent the states. It's kind of easy to remember. There's just a handful of gases: hydrogen, nitrogen, oxygen, fluorine, chlorine, and then all the noble gases. And then there's just two liquids, mercury and bromine. And then all the other elements are solids. The elements that have only been synthesized, artificially made, have a little disk. And most of those are the radioactive elements down here. All right, now I know you've seen this before. The green is the naturally occurring elements, and the purple are the synthetic elements. It's a better visual here where we put the intertransition elements where they rightfully belong. And you can see that all the elements after uranium, referred to as the transuranium elements, these are synthetic elements. These elements are not found in nature, and they're artificially made in particle accelerators. They are radioactive and readily decay, have very short lives. Now, there's a few elements in the main body of the periodic table that are incredibly rare, and they are often tagged as being synthetic as well. Just FYI, just a few of them. Okay, that is the end of notes. A short one, huh?